Swayam Prabha. Digital India. Educated India.
All right. So in the last sort of session, what we talked about was around the architecture of hard disk drives and SSDs, a little bit about workloads as well. What I'm going to do now is shift gears and kind of move over onto the software sort of side of things, right? And what we've talked about so far is essentially, so if I kind of try and draw this out, we have talked about disks over here, and these could be HDDs, these could be SSDs, they could be something else. Right? If I think about an application that is running over here, right, has, as we talked about before, there is the compiled binary or the sequence of instructions for this application that is sitting. Can you hear me? My mic was somehow muted.
Yes, sir, you're audible now.
Okay. All right. So the application is running the set of instructions, the compiled instructions are sitting were sitting somewhere on the disk, and the associated data as well, right? But all of this information has to be retrieved by the application, or has to be retrieved to the application by some entity in the system, such that the application can start executing, make forward progress, and so on and so forth. Right? So typically, the entity that kind of does this for the, or rather on behalf of the application, is the operating system. And even within the operating system, we have a very specialized subsystem that is responsible for dealing specifically with the storage sort of medium, and that is known as the file system. Right? So there's a specific subsystem of the operating system that is called the file system, that is responsible for managing information that is stored on the storage medium. Okay, so this is what we sort of talk about in this section, right? So there are essentially, I mean, if you look at it from a very high perspective, there are three things to an application's execution. One is the application itself. The second is the logical arrangement or extraction of the instructions as well as data from the storage medium by somebody, which is the file system component of the operating system. And the third is the actual storage of that information on the storage media, which is something that we have looked at in the previous lecture. Right? So this is what we have already talked about. And this is essentially what we're going to talk about right now, is the component of the operating system that is responsible for managing this storage media. Right? Okay, so essentially then the question becomes, so one thing that we saw in the previous lecture is you can read and write information from disks, whether they be HDDs, whether they be SSDs. You can read information, you can write information. Why is it that you need this middleware, this file system as a part of the operating system to manage information on your? Why do you even need a file system? I can issue reads, I can issue writes to the disk drives. Why do I need file systems? Somebody wants to take that? Maybe. Okay. If somebody wants to take that, otherwise I'll sort of hold copy. Okay, let's see. Maybe this time Himangi. Do you want to take this? I can't hear you, Himangi, if you're speaking. Nitesh? All right, Rahul, go ahead, please.
So basically, HDDs and SSD store all the data at very lower level, like at lower level. So basically, file system is kind of providing us an abstraction that we can directly deal with all the saved files at user-friendly level, that higher level. We need not to go to that lower level. We can, file system provides us that abstraction.
Absolutely, right? So this is essentially exactly what I was getting to, right? So the idea here is that although you can read and write to devices directly, let's say, I mean, you're allowed to, but I mean, for the sake of discussion, let's assume that you're allowed to. Um, Imagine what you'd have to do to write or read information from a hard disk drive. To read information from a hard disk drive, the application would have to say, well, go to platter 0, track 35, sector 25 on that track, and then give me that 512 bytes of information that is sitting there, and I'll interpret it in some fashion. Right? And then you'd have to keep doing this for every piece of information that is sitting there on the disk, and you'd have to sort of do the exact same thing for writing information on the disk as well. Right? So even though that is technically possible, it is a very non-optimal way of kind of doing information exchange from the storage medium. Right? So that's point one. There are the obvious management issues for operating systems here as well. So if you give the responsibility of managing the set of storage devices that you might have associated with your entire system, it is probably going to be able to do a better job than every application trying to read and write, different sectors on the hard disk drive themselves. And there are obvious security issues there as well, right? I mean, if I being the application have access to reading and writing any platter, any track, any sector on a platter, I can do whatever I want, and that's obviously not a good thing because I might go and overwrite somebody else's information if it's a time shared system to some extent. Right? So those are the obvious management side of things. From a more user-centric perspective, so at the end of the day, all of these computer systems are being used by humans, and we as humans are more comfortable with the arrangement of information in a certain fashion. Right? So before computers came into being, or even today to some extent, where things are maintained in pen and paper, or information is organized as files or file folders, and then information is kept within papers within those folders. And so there's a logical organization of information that has kind of ported itself over from the non-computer times into the modern computer systems by and sort of helped design file systems to some extent. Right? So we as humans need information abstracted out to some extent to be able to make sense of it, and that is one of the reasons why we have files and file systems. The primary, one of the primary reasons of these things being there is because humans need information to be sort of collated in a certain fashion, right? So when we're talking about computer systems and files specifically in the context of computer systems, there are certain notions that we associate with files, right? And that's potentially true for non-computer system files as well, right? So what we really want a file to do is to be able to reliably store data, right? If I write a particular file and store some information in it, I should be able to retrieve that exact same information at a later point in time, until unless I go and change that information. I should be able to locate that file, right? I mean, as we had talked about before, storage medium are kind of divided into these notions of track, sectors, basically hard disk drives, track, sectors, so on and so forth. Whereas humans understand natural language, right? I mean, I understand English, I understand Hindi. I would rather not, if I can arrange, if I can sort of avoid it, rather not have to deal with tracks and sectors and platter numbers. I would rather say, go to this folder and give me this file than something else. So I should be able to locate that folder and that file, and I should be able to sort of name things and then find things using that. Right? So these are the two large expectations that are, or that we expect the files to do. What we also expect And this is a combination of the expectation from the file system as well as from the storage media. If I write something to a file, it should not change unexpectedly until unless I kind of write to it or I want the content to be changed in a certain fashion. The content should change as and when I request them to change. So if I say, change these bytes within a given file, they should actually change. And the next time I sort of read that information from the medium, those changes should be reflected. Right? So these are the things that we kind of logically at a very high level kind of expect from files. And the reason why I'm mentioning this is because that translates into what or how do we do information or how do we store information or how do we design file systems in order to be able to do that. And that's true with any computer system is you need to sort of have a very clear sense of what the system is supposed to be doing. Right? So as we talked about before, we could potentially not have file systems. We could potentially have just applications storing low-level reads and writes. The first thing is but that low-level interface is very limited. Right? So when we are reading and writing information from disk drives, this is typically done in large blocks, 512 bytes. Can anybody sort of tell me why we're doing large blocks? I think I mentioned it briefly in passing. So this is 512 byte blocks. This could even potentially be larger, maybe even 4 kilobytes. And let's consider my storage medium for the time being is an hard disk drive. Why would I want to read information at a larger data, 4 kilobytes, 512 bytes, but not at a smaller, let's say, a cache line granularity, which is 64 bytes? Okay, anybody want to take that? Okay, maybe I'll just follow people. Let's say Pallavi. Sorry, if I'm calling a name twice, I don't remember what I called on the last time.
Excuse me, sir. Can you repeat it again?
Sure. The question is, why do if I read something from a disk, why is it that I want to read it in 512 byte chunks or 4 kilobyte chunks and not, let's say, 2 bytes at a time? Do you want to take that, man?
Yes. So, like, if we take it as a chunk, we will be like instead of going from so we are taking a chunk, and that all chunk will be covered in a single cycle only. Like it will be going from one memory to the next level of memory. So in this case, what we will be saving is that we will be for our time for going back and forth to get all the data, we will bringing all that chunk to a nearer memory
Sure, but
so that we can use it further.
that's true. But why, let's say, 4 kilobytes? Rahul?
So basically, when we keep the size constant, there are some optimizations that we can do. But on the other hand, when we if we take it dynamically, that 3 kilobytes or 4 kilobytes, whatever it comes, then there are some constraints that we get, and those constraints needs to be addressed while accessing the data. So basically, keeping one constant size gives us some optimizations, might be.
Okay, so that's one point, and sort of that's getting further ahead. But what I really wanted to kind of point out is it's a slow medium, right? I mean, if you look at the pyramid that I had in the previous lecture, it's a very slow medium. Even if it's an SSD, if it's an HDD, it's a very slow medium, order of milliseconds. Even if it is an SSD, it's relatively slow compared to the next level, which is the DRAM, right? If you're going to a slow medium, you might as well optimize for getting as much information out from that slow medium as quickly as possible, than having to do that in small bite or small sized chunks, right? So if I'm spending the time of moving the actuator arm and going to a particular track, I don't want to read one bit information or a byte of information out, right? There is some amount of locality that is there in the program, some spatial, some temporal, don't really know, but there is some amount of locality there, and because I'm going to a slow medium, I want to read as much information out as possible. Right? So that's one of the reasons why anytime you go to a tertiary storage medium, you'll be reading out larger bite-sized chunks, right? So again, as you go from the CPU all the way to storage, the amount of information that you kind of read out from each one of these successive sort of layers in the hierarchy increases, right? Anyway, so that's kind of besides the point, but I thought I'll sort of point this out, right? So as I say, you are reading larger size chunks from your storage medium, right? There is no notion of files or directories which I as a human is more comfortable with organization of information, right? So what I need to do is essentially provide this notion of files, directories, whatever it is, at some level, right? I mean, there's an argument to be made that why can't I just do it at the hardware level, and then it's a good argument to be made, but then there are again considerations around it. What file systems allow us to do is to sort of abstract out the lower level details and provide a human usable medium in addition to the other things. Sort of abstracts away the limited block level device and creates a file abstraction, right? So I have this nice little middleware layer called the file system that, irrespective of whatever my underlying storage device is, hard disk drive, SSD, something else that comes along tomorrow, is still able to give me this notion of, this notions of directories, files, and everything else that comes along with files, or that I expect from files. All of that is kind of implemented purely in software. So that's one of the interesting things about file systems is that they're implemented completely in software. Again, that's kind of expected because they're part of the operating system. Right. So again, as I said, CPU and memory.
Excuse me, sir.
Yes. Right.
Can I ask a question?
Sure.
Yes, sir. So, we discussed in the first point. So let's suppose we have three levels of hierarchy in the memory, and then we are going to the registers. So in the first level of hierarchy, we have the slowest one like HDD. From there, we will be getting into cache, second level of cache, first level of cache, then second level of cache. Then we are going to the register, which are the fastest. So in the first HDD, we have an HDD. So we will fetch 4 kilobytes of a block to the cache, right? And then
No,
from 4
not all.
kilobytes from the cache.
Right. So again, typically when you fetch stuff from hard disk drives, not all of that goes into your CPU caches, right? So if you're reading out large files, a lot of the times you would read 4 kilobytes worth of information, and then that information is buffered somewhere in your main memory, right? And only a small portion of that 4 kilobyte chunk that you read out of a hard disk drive is eventually going to show up in your on-chip caches, and what shows up, or which one of or which part of that 4 kilobyte chunk eventually lands up in your on-chip caches is a function of what your program behavior is, right? What part of that 4 kilobyte piece of information is your program touching the most, which makes it the hottest and sort of puts it into the on-chip caches, right? So typically you read some information from your HDD, goes into the memory, that all 4 kilobyte is stored there. A part of that goes into your on-chip caches, and it might go or it might traverse the entire on-chip cache hierarchy. It might only go to some portion of your on-chip cache hierarchy, but that's completely a function of how your policies for on-chip caches are implemented. Does that make sense?
Yes, sir. So, just adding to it, like if we have some program which is fed in that, like we fetch from HDD 4 kilobytes, and we have our program in the first 1 KB written in 1 KB. So when we fetch from 4 kilobyte to our RAM, then from RAM we will fetch from 4 kilobyte to 1 kilobyte to our uh, caches, and from then 1 kilobyte we will feed it to our main memory inside the processor. So where do we
Wait,
exactly
memory
this
inside
file
the
system fit
processor? What
inside?
does that mean? What do you mean memory inside the processor?
The instruction memory from where we will be feeding into one and one registers, from where the
So
program counter
you mean
will be going.
instruction caches?
Yes, sir, instruction caches.
So
So
okay.
where file system lands here, like
So if any operation that you have to do, so if it's not a swapping operation, which is a completely different part of the disk, if you're reading any information from the hard disk drive, you typically go in through your file system operation. So anytime you say, I want to read some information, let's say I want to read a binary program out of my disk, this binary program, your compiled binary, is essentially sitting somewhere on your file system, right? So it's in /user/home/whatever. And then eventually in some directory, it's a.out. And you say, I want to read that a.out. Reading that a.out essentially goes through your file system. That entire binary is read out, put in memory somewhere, right? And then you sort of said that your entire 1 kilobyte program is brought into your on-chip caches, which might be true, but not necessarily at the same time, right? So if your entire set of instructions is 1 kilobyte, when you read your a.out, it's laid out into memory. And let's say for the time being, all of that 1 kilobyte is laid out in the memory at the time when that binary is read out. But that entire set of 1 kilobyte instructions does not land up in the instruction cache all at the same time, right? I mean, you're fetching instructions one after the other. So you fetch instruction, some of that goes into the instruction cache, goes to the CPU, the pipeline, and gets executed, so on and so forth. Does that make sense?
Yes, got it. Yes, thanks. Got it.
Cool. All right. So one thing that I'll also point out over here is that because file systems are written typically completely in software as a part of the operating system, and that is one of the reasons why you have such a large variety of different kinds of file systems, right? So I mean, if you think about it at a very high level, there are a few set of things that file systems need to provide from the user's perspective, and there are a few set of things that the file systems need to provide from a storage system management perspective, right? And then the storage system management perspective, so the user's needs don't change as much, right? So if I'm a user and I'm sort of interacting with the file system, I expect files directly, so on and so forth, right? That doesn't change. What does change is how the underlying devices sort of evolve over time. HDDs become different kinds of HDDs. They become into SSDs. They become into NVMe SSDs, so on and so forth, right? So the underlying devices evolve, and the way these devices have to be managed also needs to be changed. So for example, certain things that were not a factor that needed to be considered in, let's say, designing a file system for hard disk drives now need to be considered while designing a file system for the solid state device. For example, lifetimes of sets, right? In the hard disk drives, the assumption is that you can read and write to any piece or any location on a hard disk drive as many times as you want, whereas that's not necessarily true for SSDs, where you can only write to each and every cell a certain number of times before that sort of dies away, right? So again, because different or the assumptions about the underlying hardware change as and when hardware evolves, you have all of these different kinds of file systems that are present that are trying to optimize different things in the implementation, right? So again, reliability is one of the key factors in designing file systems. Especially when I say disks fail all the time, this is very, very true for hard disk drives. I mean, we talked about how the disk head crashes into the platter more frequently than you'd like to be, and this can potentially be a very common phenomenon, right? So the file system needs to be cognizant of the fact that this can potentially happen, and it has to take appropriate steps, possibly within the same disk drive, to make sure that the data is reliably stored, right? Again, as I said, the files need to be located, right? I mean, this is something that we have kind of expectation from files we have kind of discussed, right? So now the big idea or what we need to do is sort of think about how do we organize information, right? So we have these notions of files, right? So I can create file 1.txt, and let's again assume an imaginary system where I can only have a large number of files, right? So or large number of text files. I can have file 2.txt, so now I can have file, n.txt or whatever. These are for a very large, I have a large number of files. Now the question becomes, how do I organize this information, right? Again, remember, all of this information is going to be stored on the device, which by itself is a very slow medium. So I also have to optimize for performance to a certain extent, which also needs to be considered while designing the file system. And when I say designing the file system, which essentially translates into what data structures do you pick for storing various kinds of information, right? So anyways, so let's say I have a file, I have information where there is a lot of files that are, a lot of text files that are present. The most or the most naive way of organizing information would be I have a root or I have one, let's say, folder or one directory where I organize all of these different files. Right? So I have, this is file 1, this is file 2, this is file 3, and this is file, and so on and so forth. Right? So this would be the simplest mechanism of organizing information. So, but that again becomes very, very unmanageable very, very quickly. So what I'd rather have do is essentially break that down into a hierarchical, right? So this is essentially a single root where from which all my files hang off of. But what I'd rather want to have is a more sort of a tree-like structure where I have some root, and then there are multiple children for this root, and then eventually to get to the files, I have to traverse this tree. And this is essentially, and this fits in well with the notion of how we think about organizing information as well, right? So I have this one large file closet, right? And then I say all the A to M files go in the top drawer, and all the rest of the letter files go in the bottom drawer, or something of that sort. Right? So I have this logical, when even I'm trying to organize my own information, I have this logical sort of thing in my head as to how I organize this, and that kind of fits in very well with this tree-like stuff. Right? So I go to this one place, and then from depending on what kind of information do I have to look up, I branch out in the appropriate side of the tree accordingly. Right? So again, this is essentially what I'm trying to point out over here. What essentially that's saying is that I have some sort of a hierarchy that is kind of built in, right? So I have a rather than having one root and everything hanging off of that root, I have some sort of hierarchy built in, where I have one root and then I traverse this tree-like structure to get to the information that I need, right? And if you sort of think about it this way, if I go back to this tree-like structure, this is the root of what I call the root of my file system. And when I traverse this information, or when I traverse this tree, every non-leaf node that I encounter is essentially what can be considered as a directory. Right? So we will talk a little bit more about directories and how they're different from files in just a bit. But then again, when I think about directories, they are nothing but sort of pointers to other locations. So I'm trying to organize information in a hierarchical structure, which essentially means I need to sort of chase down pointers to some extent. Each one of these structures that are present in my tree that is a non-leaf node is essentially a directory, which is, again, you think about it as a container of other information. Right? So if I go back over here, if I think about it this way, if I consider this node to be a directory, then this box is nothing but a container of information with the root of that information being this particular, right? So again, I can organize information as sort of directories that are pointing to other directory, and eventually I traverse down various directory or various hierarchies of directories to get to my essentially file. So basically, I can have things like /user /manu /letters /f1.txt, f2.txt, fn.txt. Right? So this is a better way of organizing information, and each one of these. So this is essentially the root of my file system. Oops, this is the root of my file system. There is another directory within that root. Then there is another directory. Then there is another directory, and then there is a set of files which are essentially the root. Now then we'll talk about how sort of these things need to be organized. But that's essentially the notion of how file systems, which fundamentally are nothing but just data structures, right? I mean, these are data structures that keep track of information on your storage device, and that's how these things are essentially arranged, right? So again, these are hierarchical file systems. You can think about them as implementing namespaces, right? So the entire file system is just one namespace, right? So that's why you can have potentially multiple file systems even on the same computer system. So you can have one disk drive which is configured with, let's say, ext4, and another disk drive that is configured with xfs or something. And these are two completely different namespaces because they're kind of independent of each other. Right? So again, it's important when you're organizing information in a hierarchy that this information needs to be organized into an acyclic graph with a single node, which is a tree, right? Which I just talked about. Why do you think that is important? Why should I have this information kind of, the choice of data structure should be a tree and it should be acyclic? Any comments there? So, okay, so let me just quickly answer that. Assume you have a single data structure, right? I want to get to this file. Remember, we had this thing about where each one of these files should have a unique name, right? So when I was looking at this particular file name, each one of these files has a unique name. If I a unique canonical name, I can sort of append to the file name the complete path, and this f1.txt is going to be different from an f1.txt that is present in some other directory, right? And that's why they don't allow you to create the same name file in the same directory, because then it's not locatable by a unique name. Okay, so let's say and in this case I said that the root of the tree was this directory called slash. Now assume that that was not the case. Assume that there was no root of the tree and there was a cycle in the graph. I wanted to get to this directory. What is the unique name of this directory? I don't really know, because I don't know where to start. I could start here and I could say you used to love them, right? Or I could start here and I could say me, you used to love them, or something of that. Right? Because there are multiple names for the same file, and there is no one unique name for this particular file. In order to be able to fix this problem, I mean, this is a relatively easily fixable problem. Right? I break the cycle, and then I just say, or I just pick one of these nodes as the root node. Right? So essentially, I say I'll pick this as the root node, and then I'll break the cycle. So now, every time I need to get to a directory or I need to get to a file, what I have to do is essentially start at the root node and navigate to that file using the pointers that are sort of stored in the data structure or the file system data structure. Right? So in this case, the unique name for the file is going to be you used to love, something of that. Right? And it's unique because there are no cycles. I always start at the recognized root of my file system data structure, which in this case is this blue node called U. And I can make the exact same analogy for actual file systems, where I say I have a root node for all my file systems, and it is slash. Right? And again, I'm not talking about Unix style systems. So slash is the root of, let's say in a Ubuntu installation you might have, slash is the root of your file system, and everything is kind of hanging off of that root. Right. So again, let me just quickly iterate over what are the file system design goals. So again, we have to finally translate file names into file contents. Remember, all I had said up until this point is I have user manu letters f1.txt. Okay? All I'm saying with this sort of choice of data structures is, for this particular file, starting at this root node slash, I'm going to have a unique name for this file. Right? So this is the unique name, unique canonical name for this file. I have not mentioned anything about what or where are the contents of f1.txt located. Right? I mean, eventually f1.txt contains a bunch of information that is located somewhere on the disk. How do I find that information is also something that should be considered. And again, I need to be able to look it up properly. I should not miss any information, and I should be able to look it up efficiently. It should not take me forever to sort of read this particular file. So I have to translate file name. So I need to have a unique file name, and then I should be able to translate that into the contents of that file. I should be able to do all of these things because my files might be expected to change. If I have, let's say, if this, rather than having f1.txt, it was called my daily journal.txt or something of that sort. In that case, I'm going to, the expectation is that I'm going to change this file daily, and that file might move, grow, shrink, depending on how I'm trying to arrange my information in a given year, so on and so forth. Right? So if I have these kind of requirements, my file system should be able to do that. Again, you have to optimize access to single files. As I said, if I'm trying to look up f1.txt or mymovie.mp4, I should be able to look that up quickly. I should also be able to optimize access to multiple files. Right. So, for example, let's say you have compiled Java project. And you have a bunch of class files, and then these class files are sitting somewhere in your directory. In that case, all of these class files are related, and each one of these are potentially going to be accessed when you run your Java project or something like that. Right? Access to all of these class files should also be optimized by the file system because they are, again, multiple files, as I said before, and they are related to something in this case. And you can think about multiple examples where the kind of files are actually related. Right? Again, as I said, disks are flaky; they fail all the time. So the file system design should, as a first design principle, be able to sort of account for the fact that failures happen and be able to survive those failures to the extent possible. Right? I mean, if the entire set of platters goes kaboom, there is nothing much that can delete. Right. So again, most of these things I've kind of talked about over here, but then some of the things that might also be important from the perspective of managing information in a location or in a computer system that has multiple users. For example, permissions. Right. If I have 4 users on a given computer system that are using the same file system, not everybody should be able to access each and everybody's files. Right? So that's point one. Users should not be able to access operating systems files. So that's another sort of things that needs to be implemented. Right? So there might be attributes associated with each of these file systems. A set of files is readable. A set of files is readable and writable. There are certain set of files that are both readable, writable, or readable, writable, and executable. Those set of permissions need to be maintained by the file system itself. Right? Again, you have to have names, as I said before, and they have to be organized in some sense of a hierarchy, such that each and every individual file has a unique canonical name. Right? And again, the interface and feature set remain mostly consistent. Right? So what I mean by this over here is that if I'm an application programmer, the set of calls or the set of interfaces that I have available to interact with the file system mostly remain consistent, right? So I have, let's say, open, read, write, so on and so forth, else, for example. What different file systems differ in is how they actually implement each one of these. Right? So I could, bunch of people sat down together and said, well, this is going to be the standard interface to the file systems. Again, if you look up the POSIX standards, that's eventually what it boils down to. There's a standard set of interfaces that is provided. These are the interfaces, these are the parameters that they should take. Now, how you implement it is up to you. So Windows implements it differently, Linux implements it differently, HP Unix implements it differently, so on and so forth. So the implementation is left to the implementers of the file systems, as long as the interface remains consistent. Right? It should not be the case that I write a program for ext4 and that doesn't work for XFS just because XFS doesn't support the set of interfaces that ext4 supports. That should not happen. Right? Now, this is actually a hard problem. Right? I mean, writing file systems is hard because of all the things that it has to take care of. Right? And I'm going to quickly sort of try and give you a sense of why this is hard with an example. Right? So there's a process. It has a bunch of open files, and it wants to write data at the end. Right? A relatively simple thing. If you're an application programmer, you could write 20 lines of C code to sort of do this. But from the perspective of the file system, think about all the things that it has to do. Right? So, okay, animations happen now to follow. But anyway, first, and again, assume that I have my hard disk drive as the storage medium, keeps the discussion simple. So first, I have to find empty disk blocks where this new set of information can potentially be written. Once I find these disk blocks, and remember, these might not be available, so I have to somehow make them available if disk blocks are not available. Once, let's say, I have the disk blocks available, I have to make sure that now these 2 disk blocks that the new set of information has to be written to are now associated with this file. So if I'm writing to this file /user /manu/f1.txt, right, and I want to write 2 blocks worth of information, and I find those 2 blocks, I have to now associate these 2 blocks with this particular file, and that has to be kept track of by the file system. You have to adjust the parameters or whatever metadata that is being kept track of for this particular file accordingly, which in this case is just the size of the file. So you say F1 has now grown by a kilobyte or something like that. So, and then eventually have to copy the disk, because this information, this 1 kilobyte worth of information was generated by the process that is trying to write. So now you have to actually copy that information in the 2 disk blocks that you have found, right? And again, this is not a comprehensive list of things, but it gives you a sense of what all needs to be done to just write 2 blocks worth of information, right? So from the perspective of the application, this is relatively simple. Write 1 kilobyte worth of information. From the perspective of the file system, it has to do a whole bunch of things, because now it has to interact with the disk drive as well, right? So from the process of from the perspective of the process, all of these things are happening synchronously, which essentially means I say write and the write happens, right? But from the process of from the perspective of the file system, each one of these things has to happen one by one, and probably even sequentially to some extent. If I can't find 2 extra blocks, I can't do the next set of steps that have been listed over here, right? So eventually it boils down to a sequence of many asynchronous operations, and they have to be completed. All of them have to be completed for that one simple operation from the application level, which said, write 1 kilobyte worth of information, to actually be completed properly, right? And again, there's both a consistency and a performance problem. So we will take a look at about how this is so the performance part of it is relatively straightforward, right? I mean, you have one operation, it is broken down to 10 different operations, and each one of these operations is sequentially dependent on the previous one. Of course, you have a performance problem, right? And it's even worse, because now you are interacting or doing these set of operations on a medium that is super slow, right? I mean, I'm doing all of these operations on a hard disk drive, and I have to do 10 operations, right? So again, it becomes a performance problem. So I have to, when I'm writing or when I'm designing file systems, I have to make sure that I have to reduce the number of steps, or reduce the sequentiality of the steps as much as potentially possible, and that gives rise to interesting optimizations that can be implemented in the file system, right? It's a consistency problem as well. For example, let's say I found those 2 blocks, right? I increased the size of the file by 1 kilobyte. I eventually, before I could write those 2 blocks onto the disk, or the actual information of the two blocks on the disk, the power went away, right? So now I have 2 extra blocks that are associated with that file. My metadata says that, okay, this file is 1 kilobyte than it's actually supposed, or 1 kilobyte bigger than it's actually supposed to be. But the last 2 blocks of the last 1 kilobyte worth of information is just not there, right? So there's a consistency problem as well, and this is something that the file system has to sort of account for while sort of writing all of this, or while you're designing the file system, right? So again, let me give you also a sense of how information is going to be organized, right? So we have a sense of logically how information is organized in a file system. So you have this namespace, you have a root of the tree, you have the set of directories that you have to traverse to get to a file. And now I have to sort of think about is, let's say I'm able to do all of that. I'm able to locate the file. How do I read out the contents? Because eventually the disk provides the interface which is reading and writing at the granularity of sectors, which are 512, or sectors or blocks of 512 byte entities, essentially, right? So what helps in this regard, and then this is irrespective of whatever medium that you're using, hard disk drive, SSDs, doesn't matter. But you have to think about the storage medium as nothing but a collection of blocks, right? So I have a 512 gigabyte hard disk drive. Each one of my blocks is 512 bytes, right? So I have 1 giga blocks in my system. I have 1 giga places that I can address on my storage medium. And you can sort of think about this, or you can think about any storage medium in this fashion, right? So I have this large sort of rectangle area, which essentially represents my entire hard disk drive. And then I have these small chunks, which essentially represent different blocks, and they keep on. Right? So this is essentially logically how you think about storage devices as just nothing but a collection of blocks. Right? Now, this collection of blocks, what I'm going to do when I'm going to sort of start thinking about designing file systems, is I'm going to break them into 2 types of blocks. So each one of these, from the perspective of the disk, is exactly the same. Right? It's a 512 byte chunk that can store 512 bytes. That's it. But from when I'm trying to design file systems, what I'm going to think about is essentially think about as, oops, let me see if I can find this. What I'm going to think about is I'm going to sort of differentiate some blocks from the other blocks. I have these set of blocks that are there. I'm going to say some set of blocks are going to be special blocks, and I'm going to call inodes. I'm going to get into what inodes are. But these are special blocks that don't contain data, but contain metadata. Right? And the rest of the blocks that are there are essentially data. And each one of them is still 512 or some size, some fixed size that comes and pre-decided with your device. Right? So, okay. So now what I'm going to do is, so I have this large set of blocks. What I have said is these are the set of blocks that are special. I'm going to call them inodes, and the rest of the blocks that are there on the system are regular data blocks. And the reason why I sort of differentiate between inodes and data blocks is because they serve different purposes. Right? Again, as I said, remember, file system is nothing but a data structure that has to be made persistent on disk, which essentially, I mean, if it's a data structure, you have to have associated information that is sitting. Right? I mean, if you have to do pointer chasing, you have to store those pointers somewhere, and those pointers actually in this particular case are stored on disk. So what I'm going to do is I'm going to sort of think about my my blocks as two things, which are inodes, and the other ones are data blocks. Right. So what I'm going to also assume for and I'm going to take ext4 as an example, and this by and large remains consistent, or this organization kind of remains consistent across different file systems as well. Right. So I'm going to have one inode per file, and this inode is, let's assume it's 256 bytes, and how big an inode is also a file system design decision. So ext4 decided that each 256 or each inode is supposed to be 256 bytes. So again, depending on what the assumptions are about your underlying storage device, how big blocks are, how big sectors are, so on and so forth, you can fit so number or n number of inodes in given sector. Now, inode is special because it does not contain data, but it contains metadata, and what metadata has is set of information like this. Where are the data blocks located? Right. So let's say my f1.txt that I had previously mentioned is a collection of 4 blocks worth of information, and those blocks could potentially be located anywhere, as I had said before. But the inode for that particular file essentially knows where all those 4 data blocks are located and stores that information within itself. Right. So if I can locate the inode for this file, I can figure out where all the data nodes or data blocks for this particular file are located. Of course, there are permissions, and that serves an important purpose. Rather than going all the way to the data blocks first and then figuring out the permissions of each and every data block, I first go to the inode. I look up the permissions of whether this particular process or this particular user has access permissions or the kind of access permissions that it needs for this file, and I can just store that in the inode. If the user does not have the permissions, I can just fail right away without exposing the data to the process of the user. Right? Of course, there are timestamps, and they are essentially useful for a multiple number of things. And then each one of these inodes can be located by essentially a number. Right? So if I say, okay, on my hard disk drive, I'm going to have these many inodes. Inode number 0 is located here, 1 is located here, 2 is located here, so on and so on. Right? So for the inode or the location of the inodes is fixed beforehand, which essentially to some extent puts an upper limit of how many files I can potentially have in my file system. Right? And there's an obvious trade-off there. If I have a large number of inodes that I have dedicated, which just store metadata, I'm taking those set of blocks out of circulation for storing actual data. Right? So the number of data blocks that I have obviously reduces. Now, if I take a very small number of inodes for my file system, then I have then I limit the number of files that I can potentially have in my file system. right? So again, there's a trade-off there. And again, each and every file system might kind of make the trade-offs in some fashion, depending on what it is trying to optimize. If you're interested, go try this command out. This works on my system because my hard disk is dev SDA1. We might have to change a little bit about um, on your actual machine, right? And it gives out a whole bunch of information about how your file system is actually formatted. Right, so as I said before, inodes are created at format time at well-known location. So if I say I'm going to format my hard disk drive with ext4, ext4 comes built in with a set of assumptions about how many inodes are going to be there, and they are sort of going to be located at known locations, right? Because anytime I need to go to a file, I need to first go to its inode, and to be able to get to an inode, I need to know where it's located, right? And that's why they need to be at kind of well-known locations, right? One thing to sort of remember is that inodes or data blocks, they're all blocks, right? So it might be the case that your inode, and again, going back to the original assumption where I had this hard disk drive with multiple platters, right? So let's say my inodes are all located on platter 0, but the particular file that I'm trying to get to is located, or all the data blocks for that particular file are located on platter 3. So there might be an obvious case where your inodes are located at one place and your data blocks are located somewhere else, which essentially again adds to the latency, right? So if you have to go to the disk to first locate the inode and then locate the data block, so you're sort of converting one disk operation into two disk operations just because you're adding a level of indirection because of inodes, right? And that adds latency. So there are multiple optimizations with metadata, for example, caching the metadata that have been sort of tried out in various kinds of file systems. Right. So again, as I said before, if you create a large number of very, very small files on a system, in ext4, for example, you could potentially run out of inodes. And at some point in time, even though you create, let's say, 1 byte file, right, and you create a gazillion of those, at some point in time, your file creation infinite loop is going to fail and say, I cannot create any more new files. It's not because you've run out of disk space for data blocks. It's because you've run out of the number of inodes that are actually permissible by the ext4 file system. Right, so again, that's one more trade-off that needs to be considered while we're designing file systems. Right, so again, directories are nothing but special types of files. They don't contain pointers to data blocks; they just contain pointers to other inodes, right? And they map inode numbers to sort of names, right? So if I do ls minus I on slash, it gives me what all file names are there within slash and what their respective inode numbers are. Right? You can try this out on your own system. You'll see that each one of these file names kind of maps to a different inode number. So if I wanted to read whatever's there in, let's say, slash libx32, I have to go to first inode number 54390 and then navigate from that point onwards. Right? So then the question becomes, how do I find the inode number of slash? Right? I mean, as I said, each one of these is kind of bound by convention to some extent. Inode number of slash has been fixed to be inode number 2. Right? So anytime you start at, or anytime you have to traverse a file system, that inode number or slash is always located at inode number 2. And since you know where each one of these specific inode numbers or inodes are located, you can start at the root of the node relatively very easily. Right? Well, let me just quickly give you an example of what has to happen if you want to read a particular file, let's say slash etc default keyboard. And basically, you have to figure out the inode for this particular file and then the associated data blocks once you have figured out the inode for this file. Essentially starts out with slash, right? So you know the inode number for the root of your file system, which is number 2. You go there, you read the inode number for etc. Then that lists the inode number for default, which then in turn lists the inode number for keyboard. And once you know which is the inode number for keyboard, then you can go to that inode number, read out its contents, and figure out where the data blocks for this particular file are actually located. And this is essentially what is kind of enumerated on this slide. Right. So again, given that I have a few minutes, maybe I'll take another 5 or 10 minutes to sort of complete this. But then Then let's talk a little bit very quickly about how we modify data flows, right? So we talked about how inodes are structured, but then eventually I have to sort of when I modify contents of a file, I actually add or modify existing data blocks, or I add data blocks, I delete data blocks, so on and so on. Right? So for example, let's say I want to sort of do an operation like this. I want to do read or write in a file handler, and it says you have to translate 345 to a data block within the open file to determine which block to modify. Right? So I'm trying to modify something within a given file at a specific location. I need to know which data block do I need to go and modify. So the question then becomes, what are the data structures that I have to traverse to be able to sort of know which data block do I have to read, modify, or whatever, and what are the semi-optimal data structures that I can choose to make sure that this lookup is as efficient as it can potentially be, right? So the idea is you can sort of organize all the data blocks in a linked list, right? So basically, this is your first data block, this is your second data block, this is your third data block, this is your fourth data block. As and when you keep adding data blocks, you add them to the end of the linked list. There is an obvious con here that to get to the last data block, you have to traverse the entire linked list, which is a very expensive operation. And given that all of this information is stored on the disk, you don't have to sort of do that. The obvious pro is that it's relatively very simple to implement, right? You can try out things like flat arrays. So rather than doing a linked list, you say, well, okay, there is a flat array that I have. So all the data blocks in that inode are allocated at file creation time. Right? So the lookup is relatively fast because all you have to do is go to that index and figure out which data block that you have to sort of look up. Right? The obvious con here is that you have the file size that is essentially fixed at startup time because you're allocating this set of data blocks. Right? And if it's a small file, then large portions of this flat array, which essentially contain pointers to your data block, is going to remain unused. Right? So both of these extremes are not very good. What is typically implemented, especially in ext4 and most of the file systems, is something which is known as a multi-level index, which is again based on almost all good system design principles are based on empirical evidence, observing what happens in real systems. And what people observed over time in real systems is that most files are small, but some of them can get very large. Right? So this is essentially the optimization that you have to do. The Amdahl's law here says optimize for small files, but then the ones that get large can or should be allowed to sort of do that. Right? So what typically we do is we have multi-level indexes, which says once you go to the inode of the file, you have some data blocks that are hanging directly off of that inode, and then you have another level of indirection to different inodes that in turn might point to data blocks, which essentially looks something like this. So if this is the sort of the master inode for the file, I have a few data blocks that are hanging off of that inode directly. And for small files that let's say fit in these two data blocks, it's relatively okay. But for files that get larger, which is not the typical case, what I can do is I have some regions in this inode that are dedicated to serve as pointers to other inodes if that is eventually needed. Right? So then if the file grows large, I allocate another inode, and then it can point to other sort of data nodes as well. And then you can sort of have multiple of these inodes which are pointing to other data nodes depending on how large a file needs to get. And you can sort of increase the levels of indirection here as well. So right now here is one level of indirection, which is this. But here you can think about two levels of indirection if your files sometimes tend to get very, very big. You can provide support for that, but it doesn't necessarily have to be there, and it all depends on what kind of things or what kind of requirements a file system has. Right? So again, there are obvious pros, no real cons for these type of multi-level indexes, and these are the ones that are mostly used. So scales up with the size of the file. Offset lookups are still relatively fast because most of the time you're just sort of hopping once, and only for large files you're hopping multiple times to get to it. So again, works out very, very well. One thing that I'll quickly mention is, because I've kind of run out of time, is one quick optimization that is also implemented by most file systems. Right? So again, what I briefly wanted to mention over here was the fact that file system is nothing but a data structure that is residing on disk, right? And again, if everything resides on disk all the time, then it is obviously a performance problem. What most file systems do in this case to get over this particular bottleneck is to make sure that they utilize some other medium that is also present in the system, which typically is your DRAM, to sort of buffer or cache things that might be used frequently by most file systems or most files, let's say. Right. So what you can potentially do is what we let me just quickly go back over here. This one over here. Right. So far, what we had sort of talked about was this stores your instructions and data. Your instructions are eventually laid out over here, which then sort of follows the one-to-one path of in exchanging instructions and data within the CPU, where the instructions actually get executed. Right, and that was the entire function of the DRAM that we had assumed till now. What I'm saying now is that rather than just assuming that DRAM is only going to store the address space of the running processes, I'm going to carve out some of the space on my DRAM and use it for or as a special place where I can store things that help speed up the operations of my file system. Right? So now your main memory is actually being used as two different things. A part of it, which is this part over here, is actually being used as main memory, which stores the address space of the various processes, whereas this part over here is essentially being used to cache or buffer things from your file system so that those things, right, for example, inode contents, can be located relatively quickly at DRAM latencies as opposed to disk latencies, right? And that remains true irrespective of whether you have your hard disk drive or your SSD as a storage medium, because as compared to DRAM, they still remain 2 to 5 orders of magnitude slower. So that's why you have this special place carved out of your DRAM, which is known as the buffer cache, right? And the buffer cache essentially is a region of your DRAM that is managed by the file system. And then depending on where you decide to implement the logic of a buffer cache, you might be able to sort of cache different things, right? Cache or buffer different things. For example, let me just quickly give you one example if I can, and then I'll close because it's been 1 minute, right? So again, I have this application over here which sends requests through what is known as the virtual file system. And let me not just go into the details of the virtual file system, but then assume that there is this one extra layer that essentially sort of intercepts all the requests to any file system that needs to go and then reroutes them appropriately to the right file system, which is then eventually routed to the correct disk. Right. So now, in order to be able to cache things, I can implement my buffer cache in software at 2 different levels. The first level is right below my virtual file system or right above my actual file system, which is this layer over here, in which case the buffer cache would be able to intercept all the read and write calls to all the different files that are being sent through the virtual file system. And it would be able to make decisions of what to cache and what not to cache on a file basis. Right, so it knows, okay, this file is being touched and that many times, read, written, whatever, and then can cache or prefetch even to some extent things appropriately, right? And that's one place where the buffer can potentially be located. The other place that it can be located is essentially at just above the disk and at the or below the actual file system. At this point, the entire notion of file systems has now been lost, right? Because as soon as you hit or entire notion of files has been lost, because as soon as you hit the file system takes your notion of file and converts that into the notion of disk blocks that we had seen before, right? So in that case, the buffer cache is only able to see which disk blocks are being accessed, read, written, so on and so forth, and that in turn determines it can only cache or buffer things at the granularity or at disk blocks, and it cannot leverage any file-based information that it would have been able to leverage if it was sitting at the level above, which is essentially just below virtual file system and between the actual file system, where it can actually implement all of these, rather intercept all of these different calls and get a sense of what needs to be done at a or what needs to be buffered at a file level, right? Okay. So with that, I'll just quickly close. Yes. So this was my last slide for this session.